Okay, let's talk about how many solutions a quadratic can have. So this is titled types of solutions. There's 3 types we can deal with, so let's get started. Number 1, so we want to build a perfect square that kind of looks like this. So I'm going to start by just building a generic box. I know that this first box is going to have that x squared. So I'm going to have an x and an x here. I want to take half of that 22x, so I want to put an 11x here and an 11x here to keep it balanced. What times x gives me 11x? That'd be 11. And same thing over here, there'd be an 11. Now what goes in this main box to make a perfect square would be 11 times 11, which is 121. This is perfect, so 121 matches 121, so I'm good there. This is a perfect square. So on this perfect square, I'm going to write it in vertex form by taking the dimensions. You could say that it is x plus 11 times x plus 11, but I'm going to write that one time and just raise it to the power of 2. Keeping in mind that our vertex form normally looks like x minus h squared plus k. What would my k value be in this situation? Since I didn't write it, I can just assume it's going to be plus 0. Now that I'm in vertex form, I can put out the vertex. I'm going to change h, so make this a negative 11, and then the 0 is my y value. So if I were to sketch this, negative 11, 0 is somewhere, and just a sketch, it's not accurate, it's somewhere over here. My a value, which is normally in front in vertex form, looks like it is a positive 1. So that means there's no stretch and there's no flip. So it means it's going to face up like this somewhat. This is passing through the x-intercept one time. So that means we're going to have one x-intercept. So the vertex is touching, or it's bouncing off of the x-axis, so it's only going to touch one time. So that's one example. Let's do 2 more examples. Same method. We're going to build a box. I know this first one has x squared. I'm going to take half of my second term and put it both in there so that we have it balanced. It looks like my dimensions are going to be x and 8, x and 8. So the value that needs to go here is 64. But we wanted it to be 24. So if this 64 is in place, it's too big by how much? So it looks like it's 40 too big. 64 is 40 more than 24. So if I were to write it in vertex form, it would look like the dimensions for my box. Since that gives me 64, but I wanted 24, I'm going to minus the amount that gets me there. So I'm minusing 40. Okie doke. Vertex looks like we're going to change h, which puts us at negative 8, negative 40. That puts us in quadrant 3, which is over here. So I'm just going to do a quick sketch. Negative 8, 40 is somewhere-ish. Let's just say it's right over there. It has an a value of 1, so it tells me it opens upward. If it opens upward, and it's just a sketch, doesn't really matter where you're going, you can see that it's going to touch through the x-axis here and here. So that means there are 2 x-intercepts. The reason why I know that is the vertex is below the x-axis. And is facing up or opening up. The parabola is opening up. Okay, last example for these notes. Same method, build a box. I know that x squared goes here. This is a negative 12x, so if I cut that in half, I'm gonna get a negative 6 and another negative 6. Oops, negative 6x, negative 6x. Which tells me my dimensions are x, x, a negative 6, and a negative 6. The number that's supposed to go here is a 36. Compared to 49, well, it's too small. But how much smaller is it? It looks like to get from 49 to 36, it's about a 13 value difference. Since it's 13 too small, I'm gonna take what the dimensions are. We've got x minus 6 squared, but I'm going to have to add something to this to make it like that. So I'm going to add 13. Our vertex, we're going to change h. We get 6, keep k, put parentheses around it. That one looks like it's in quadrant 1, which is somewhere over here. So if I've got 6, 13, let's just say I let it float right there. It's pointing up because we have an a value of 1. So in this example, it doesn't look like it's going to touch the x-axis at all. So the number of x-intercepts would be none. Okay, so there are our 3 scenarios of solutions. We could possibly have 1, 2, or no x-intercepts. So a quick little sketch of all the types at the bottom of our page. Let's just kind of divide the rest of your page in 3. Morning. I'm almost done with this short little video. Just give me one moment. Sorry. All right, y'all. 3 quick little graphs. Yeah, I'll just do it later. All right, so the last one is it passing through the x-axis. So this one, it has 2 intercepts. It's going through. There's the first one, up, and then back up down the other direction. There's my second one. So these examples have 2 intercepts. We got one here and one here. Or in this example, here and here. This one we're going to use the code word as pass, meaning it's passing through the x-axis. And that's it. At the top of your page, change this to types of quadratic solutions, or from that to 3 types. So there are 3 types of quadratic solutions. The end. All right, let's answer the question, why do we complete the square? Well, to answer that question, let's talk about the forms of quadratics that we already know. We know about standard form and vertex form. Standard form is more recent to us. Standard form will tell us what is our y-intercept, meaning that if we were to plug in 0 for x, what will we get for y? Well, if we plug in 0 here, it cancels it out. If we plug in 0 here, it cancels it out. And we're left with just a c value. So in this format, that last term that has no letters next to it is going to be your y-intercept. It also tells us our stretch or our compression. And that comes from our a value. Now, vertex form, it tells us a little bit more. It tells us, well, by its title, we know it tells us that it's vertex, or HK. It also tells us our stretch and compression. More specifically with the vertex, it tells us our transformations. Transformations. So this tells us our up, down, left, and right. We know that if it is going up, it's a plus k. If it's going down, it's a minus k. If it's going to the right, it's minusing h. And if it's going to the left, we are adding h. So if you can get it into vertex form, you can give me a description of all of that. So this one does not tell us the vertex, and this one does. So the reason why we complete the square is because it helps us convert from here to here. So conversion is why we complete the square. We want to convert from standard form into vertex form. All right, let's do an example. Here I'm given an equation that is in standard form, but I want to probably answer some questions about the vertex, the line of symmetry, and other important things from this equation. So I'm going to have to convert it to vertex form. Let's start with a geometric method. So this is the method that we use with the boxes or cubes. So let's just draw a little box. I'm going to call this x squared. That's an x by x plot. Then I want to take this middle term and I want to cut it in half and put it on both sides of my box. That way I've got 1x, 2x, and 3x up here. And I've got 1x, 2x, and 3x down here. It's my job to figure out what goes in right here. Well, we know this is going to be a 3 by 3, so this should be 9. So I know that I need 9 pieces to complete this square, so I can say that this box is x plus 3 times x plus 3, which technically gives me x squared plus 3x plus 3x plus 9. I can simplify that a little bit more. I can call this x plus 3 squared equals all of this. Oops, this should be a 6. Because I combine the 3x and the 3x. Now, this perfect square doesn't match this one. So it's got more than I need. I only needed 2 individual units, but I got 9. So this is 7 too big. If this is 7 too big, that means I have to minus 7 from whatever this box is worth. And if I'm doing it on this side, I'm going to do it on this side as well. So now I've got x plus 3 squared minus 7 equals x squared plus 6x. 9 minus 7 is 2. And that's what I wanted to get. So I've taken this standard form and converted it into vertex form. So that's how we do it if we wanted to do it with a picture. Let's talk about how we would do it algebraically. So I'm going to start with my original equation. In this step, all I've done is left a little bit of space between the second and third term. So I'm gonna make little notes as I go about what I'm doing. So right here, leave space. All right. So what goes in this space? So we're going to take half of the b term squared. Half of b to the power of 2. So what goes right there? That would be 6 over 2 to the power of 2, which gives you 3 squared, which is 9. Let's move forward. So I've added 9 here, but I'm not allowed to just add 9 because I feel like it. If I want to add 9, I need to balance my equation. So I need to minus 9. So you've got to, if you add something, you got to subtract something. That's all that's saying. Now, we're going to focus on these first 3 terms here. Now that's a perfect square, so I can rewrite that as something squared. So that would be rewritten as f of x equals something squared. Well, what are the dimensions of this box? This box would be x plus 3 to the power of 2. And then we need to simplify that. 2 minus 9 would be minus 7. So how did I get here? I factored the first 3 terms. I wrote them as their perfect square, and I simplified. And then we're done. So look, this process and this process are the same exact answer. Both vertex forms match. More specifically, what vertex form is showing you is that how far away is the original equation away from being a perfect square? So this minus 7 here and this minus 7 here is just telling you the original equation I'm going to say the original function instead is 7 less than the perfect square. And that's it. Okie doke, it is time to complete the squares. So I look at my original equation I was giving. Sometimes they're gonna say y equals, sometimes they're gonna say f of equals, but we know that it means the same thing. So let's go ahead and move forward with solving this. The first step is we're gonna leave some space in between the second and third term. Now what's gonna go in there is going to be half of b squared. So you're gonna take whatever your b value is, divide it by 2, and then square it. So in this case, my b value is 8. So I'm gonna do 8 over 2 squared, which gives me 4 squared, telling me that that space has to be 16. My last step to get to here is to balance your equation. Which just means if I added 16, that means I have to minus 16. Okay, now we're gonna focus on the first 3 terms. So if I were to factor those, or write them as their perfect square, I have some options. I can either take half of 8, or I can take the square root of 16. This would become x plus 4, which is the dimensions of that perfect square. 12 minus 16 gives me negative 4. So from here to here, I factor the perfect square. And let's see, what else did I do? Oh, I simplified. This minus 4 tells me that I have 4 less than the perfect square. So I know that the perfect square should have been a 16, but they gave me a 12. So this 12 is 4 less than my perfect square. Okay, let's do example 2. So example 2, we're gonna follow all the same steps that we did up here. We're gonna do a new problem. So step 1, leave some space. So we're going to go ahead and do y equals x squared minus 2x. We're gonna leave some space because we're gonna add something that makes the perfect square, plus 12. Now it's time to take half of your b term and square it. So this becomes negative 2 divided by 2 squared. We get negative 1 to the power of 2. Negative 1 to the power of 2 is like negative 1 times negative 1. So we get positive 1. So I'm gonna add a value of 1 here, and then I'm gonna balance my equation by minusing 1 right here. Okay, then we need to factor the perfect square. The perfect square is the first 3 terms. Can't really see my 1 very well, put that a little bit darker. So this becomes x minus 1 squared. You could either take, well, I would take the half of this one because this one's negative and we want to keep that negative. And then we're going to simplify this 12 and this negative 1 and we get 11. So there's our final answer. So what does this mean? This plus 4 says that our original equation is 11 more than the perfect square. you're having a hard time visualizing what this means, you're just gonna say that, like, if you were to build this picture, we would get x squared, negative x, that would give us a negative 2. A negative 2x, excuse me. So this is negative 1x, x, negative 1. And what goes here? A positive 1. So if we take 1 out of the 12 that they gave me, that means that there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of those baby cubes that did not fit in the perfect square. Oops, it should be 12, it should be 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So just do 11 dots out there. Cool. Okay, for this video, we're going to be talking about what happens when our a value is not 1. Remember, our standard form looks like ax squared plus bx plus c. Up to this point, we've always had an a value that was 1, and the method of completing the square only works when a equals 1. So what do we do if the a value is not 1? For example, what happens if it's 2? So we're gonna get a little bit creative. We're gonna follow these steps to the side. Yes, I want you to copy down my steps and follow along with me. So if you need to pause the video, go ahead and do so that you don't fall behind. So if we're given our equation, we have it in standard form. We wanna focus on the first two terms. Can you factor out a? Well, my a value is 2. Can I pull a 2 out of these two values? Yes, I can. So I'm gonna pull out a 2 and put it in front. And this minus 5 is just gonna chill at the end. If I pull a 2 out of 2x squared, I'm left behind with just x squared. If I pull a 2 out of 8x, I'm left behind with a 4x. All right, step 2. We're gonna complete the square within the parentheses. We're just focusing inside the parentheses. Let's copy everything else as is, because it's not gonna change. Leave some space, minus 5 at the end. So I'm gonna keep this part in the front. For me to complete the square, I'm gonna do my b value, cut in half to the power of 2. So in this case, it would have been this 4. 4 divided by 2 to the power of 2 equals 2 to the power of 2, and then we're back at 4. So I'm gonna add 4, but my equation is not balanced. It says balance your equation within the parentheses. So if I added 4 inside the parentheses, I'm gonna minus 4 inside the parentheses. Okay, it is time to factor the perfect square, which is these first 3 terms. Everything else is gonna hang out. We're not gonna change anything else. Although instead of parentheses, I'm gonna change to brackets because I'm gonna have double sets of grouping values. So this in orange, this first 3 terms become x plus 2 squared. I'm gonna drop down that minus 4. So I've only really changed these, this part and turned it into a perfect square. Okay, step 4. Redistribute the a values. Remember, my a value was this 2 that I pulled out. I'm gonna put everything back in to just the brackets, not inside the parentheses. We know that there's a value inside that, or next set parenthesis, there's a 1 here. So what we're really doing, 2 times 1 is 2. Leave all this parenthesis junk next to it. 2 times negative 4 gives us negative 8. Bring down your minus 5. I've already removed my brackets. Last step is to simplify. Negative 8 take away 5 gives me negative 13. Nothing else changes. Leave it all alone as you bring it down. And there we go. So I am now in vertex form. So what do we do when we're in vertex form? Well, let's figure out the vertex. We're going to change the value of k, keep the value, sorry, change the value of h, keep the value of k. So we get -2, -13. -2, -13 is somewhere over here in quadrant 3. And we know that since there's a positive a value, it opens up. So we're going to go -2, -13 somewhere over here. And it's going to open upward. This tells me that there are 1, 2 x-intercepts because they are passing through the x-axis. Cool. We're going to do one more example. Okay, let's do another example of completing the square when our a value is not 1. In this case, our a value was a -3. We're going to follow the same steps as before. Step 1, focus on the first two terms, factor out the a value, no problem. So we're going to start with f of x equals, we're going to pull out this -3, leaving behind x squared. If I pull a -3 out of 18, that's going to give me a -6 and then bring down our x. All right, so step 1 is done. Complete the square, balance your equation. Make sure you do this all inside the parentheses. So we've got -3, oops, f of x equals -3, x squared minus 6x. We're going to add something, and then we're going to minus something to keep it balanced. And then this -23 doesn't change. So the way we figure out what goes right here is we're going to take half the second term and then square it. So b divided by 2 to the power of 2 gives me -6 divided by 2 to the power of 2. We get -3 to the power of 2, which is 9. So we're going to add 9, and we're also going to minus 9. Step 3, factor the perfect square. So the perfect square is these first 3 terms. Everything else is going to stay the same, except we're going to put brackets around the original parentheses. These 3 terms are going to become x minus 3 squared, and your -9 at the end stays there. Step 4, redistribute your a value. So we're going to take this, oops, -3, didn't copy that as negative, my bad, and distribute it to everything inside the brackets. Remember, there's a 1 right here. So we're doing -3 times 1, we get -3 parentheses x minus 3 squared. -3 times -9 gives me a positive 27. And bring down your -23. Our last step is to simplify. We're going to simplify these 2 terms. -3 parentheses x minus 3 squared. 27 minus 23 is 4. And we're done. We're now in vertex form. So we can say that the vertex, we're going to change h, keep k, 3, 4. Because this is a -3, this tells me it opens down. That negative says that there's a flip in my parabola. So 3, 4 looks like it's in quadrant 1. If I do a quick sketch, 3, 4 somewhere over here, it opens downward. And in this situation, looks like there's going to be 1, 2 x-intercepts. And that's it. Be sure to go over these notes tonight. Make sure you understand what's going on, because tomorrow we're going to start using this. You need to know how to both solve when a is 1 and when a is not 1. Cool. See you tomorrow. Bye.